Welcome to week 10. This week we're going to continue electrodynamics, this week focusing on Ohm's law. Ohm's law is a little bit different than the other laws we've been working with. It doesn't come from Maxwell's equations. It's not as much of a law as Maxwell's equations are. Okay, so let's look at what Ohm's law is. And this is going to look a little bit different than what you're used to. Okay, so how do we get to Ohm's law? Well, we start off by thinking about how current density is related to the force per unit charge. So remember, we've been working with current density J rather than total current I. This lets us be a little bit more flexible than I does overall. Sigma here in the equation is the conductivity. This is experimentally measured for different materials. But what you may have seen before, or if you look up in handbooks, which are more likely to see, is the resistivity, which is the inverse of conductivity. That's the constant of proportionality between the current density and the force per unit charge. So the force exerted per unit charge is determined by the Lorentz force, which we talked about last week. So if we just want the force per unit charge, we just have to divide out the Q. Now we can plug in a force per unit charge and find the current density. This is something that's generally true. The current density is proportional to the electric field plus V cross B. But when we're looking in circuits and when we have current flowing, it's often the case that the force from the electric field is much bigger than what you're getting from the magnetic field, oftentimes because this velocity of your charge is small enough. So then we can simplify this in many cases to get the current density equals the conductivity times the electric field. And this is Ohm's law. This is what we will refer to as Ohm's law in this class. Well, that's not what we're used to seeing. How does this relate to V equals IR, what we always teach in intro classes? Well, before we can do that, there's the issue of we haven't really talked about potential much yet. V. So I've mentioned that potential is the line integral of the electric field. Let's go back and dig into what potential is so that we can relate potential and the electric field. So if we're looking at potential in one dimension, we could say that the electric field is minus the spatial derivative of the potential. If we want to find the potential from the electric field, we would take the integral of the electric field. But in this class, we're typically working in 3D. So then the electric field is minus the gradient of V. Now we haven't worked with the gradient much. Gradient is a 3D version of slope. We've done curl and divergence, which in my opinion are both more difficult to think about than gradient. So if you're thinking about gradient, if you think about a hill on a topographical map, and if you have this hill, you have a vector that points up the slope. So if you have a vector that points up the slope at any point on that slope, that's the direction that the gradient points it. But the electric field is the negative of that, so the electric field then points down the slope. But we're not going to be working in that direction very much. We're more often going to be calculating the potential from the electric field in this section of the class. So we're going to have a line integral. So if you do a line integral of the electric field, that gives you the potential. Alright, so this is all pretty abstract. We have a bunch of formulas. It's a little bit hard to think about what this means, especially when you're trying to understand what gradient is, because we haven't talked about that much yet. Okay, so let's go and look at an example. So let's just look at the example of a point charge. So if we have a point charge, a positive point charge, the electric field points away at all locations. So if we define 2 points, we'll call this one A and this one B, and we want to find the potential difference between A and B. Okay, so to find the potential between points A and B, we're going to do a line integral. So to get started, I want you to do two things. So I want you to write down what the electric field from a point charge is. You already know this. Many of you teach it in your classes, so that's an easy step. And then I want you to figure out what dl is if we're integrating on a path between A and B. Alright, so pause the video and do that. Okay, so we all know the electric field from a point charge. Now, this is going to be something we want to do in spherical coordinates. So if we're integrating along a path between A and B, then r is the variable that's changing. So this is just going to be dr r hat. Okay, so the next thing I want you to do is to actually set up this integral. So you have E, you have dl, you know you're integrating between B and A. Let's go ahead and set that up. So this is r hat dotted with r hat, so r hat dot r hat is just 1, so we get this for our integral. Okay, so the last thing I'm going to ask you to do is to actually compute this integral. Okay, you know how to do this integral, so go for it. Okay, well the first thing I like to do is pull all of my constants out front. I'm going to rewrite 1 over r squared as r to the minus 2 because it's a little bit more straightforward to use the power rule in that form. So power rule gives us r to the minus 1 over minus 1. I'm going to cancel out those minus signs. R to the minus 1 to 1 over r. Okay, so this is what we get for our potential. So this is the potential difference between B and A. Now if you do teach potential in your classes, you may teach something that doesn't have this minus 1 over B in it. That's often because what we teach in those classes is we use an infinite distance away from the point charge as B. So that's our reference point because we're always talking about a potential difference. So if you want to set your potential to 0 for your reference, then you set B at infinity away, and 1 over infinity is 0. Okay, technically the limit of 1 over B as B goes to infinity is 0, but I'm a physicist, so I get a little sloppy with that. Okay, so that's how you calculate potential. Now we can go back to talking about Ohm's law. Okay, so how can we understand the connection between J equals sigma E as Ohm's law and V equals IR as Ohm's law? Well, one thing we can do is notice that J is a current density, so let's solve V equals IR for current. Okay, so current equals V over R. I generally find this is the more useful version of Ohm's law anyway, as you normally want to solve for the current. Okay, now I'm going to go back to the current density version of Ohm's law and switch out 1 over rho for sigma. Remember, because the conductivity is 1 over the resistivity. Okay, so now you can see the connection. Current density is going to connect to current. Electric fields going to connect to potential. And resistivity's going to connect to resistance. So you can kind of see by analogy how they're related. Now I'm going to work out an example so that you can see how we can actually use this in practice. And it's going to turn out that getting resistance from resistivity is both a function of the material that you're using and the geometry. Alright, so let's look at that example. Okay, so I wrote a lot of words just so you have all written down everything that's going on in this situation. I realized after I write this many words, I should have just typed it. Oh well. I like to teach this class like it's board work, but sometimes that's not always the best case. Not always the best decision. So we have 2 concentric cylinders. Think of them as metal cylinders. So you have an inner cylinder made of metal, then you have an outer cylinder made of metal. There's charge on each of these cylinders. There's a resistive material between them. The material has a conductivity, sigma. The conductivity is a constant. There's charge present on the inner and outer surfaces so that current can flow between these 2 cylinders. The potential difference between these 2 cylinders is maintained at V. It's just its value V. And we want to figure out the current flowing between the two cylinders and the resistance of this material between the two cylinders. So, how do we do this problem? Okay, well, step one, we need to find out what is the electric field between the two cylinders. Alright, now this we could figure out from Gauss's law. But I don't want you to have to go back and redo Gauss's law every time you're going to do one of these. What I want you to do is go back and check your notes and find a situation that looks similar to it and use the results we found before. So what we want to think about with this inner cylinder, I told you that there's charge present on the inner cylinder. So it's evenly distributed. So we can say that there's a charge density per unit length of that inner cylinder. So I'm going to call that lambda. It's not given in the problem, but you can make it up because we're going to eliminate it later in the problem. So remember, in Gauss's law, the electric field just depends on how much charge is enclosed. So if we have a cylinder with a charge density on it, it's the same as if we just have a wire with a charge density on it. And we've done lots of problems with cylinders in finding the electric field outside of cylinders. So I don't want you to go back and solve this. I want you to look it up. So this is the electric field between two cylinders. You just have your coordinate system set up so that z is along the inner axis, which is what makes sense for cylindrical coordinates. Okay, we have an electric field. Good. Now what we're going to do is use the electric field to find the current. Okay, so we know from Ohm's law that the current density is sigma E. So in that case, alright, now we have a current density. And remember, this current is flowing outwards from the inner cylinder. So the current is in the S hat direction, away from the center of the cylinder. Which is not a situation we have thought about in terms of current before. So that's kind of interesting. Okay, and we know from all that we did with Ampere's law that the total current is calculated as a surface integral of J dot dA. Okay, what's dA in this case? So it needs to be the cross-section of the way the current is flowing. The current is flowing outward from the center of the cylinder. So that's an S hat. So it's basically the curved surface of a cylinder. So that's the one where phi and z vary and S is held constant. Okay, let me know if that makes sense. Flowing outward in the cylinder, the cross-section of the current is the curved surface of a cylinder. So then we can set up this integral. J dot dA, S hat dot S hat is 1, so we have J dotted with dA, so J brings in a 1 over S, dA brings in an S in the numerator. Phi is integrated from 0 to 2 pi, go all the way around the circle. Z integrates from 0 to L. Okay, well these S's cancel out. That's nice. Let's separate this out. So I always like to pull all my constants out front. Well, all we're left with is constants. So this will be an easy integral. These integrals, we've done them many times before, so I'm not going to work them out in detail. So that gives us 2 pi L. Okay, let's write that out. Our 2 pi's cancel. Okay, we found the current. Now the reason this isn't the answer to the problem is that lambda is something we made up that we need to get rid of by the time the problem is over. So we have current in terms of the conductivity, the charge density we made up, the length of the cylinder, and epsilon naught. Okay, step 3 is we're going to find the potential from the electric field. So we have our electric field, we have our equation to calculate potential. What we need to determine is what dl is. So we're integrating between the two surfaces of the cylinder. So that means S is a variable here. Okay, we're integrating from the outer surface to the inner surface, from the outer cylinder to the inner cylinder. So we're integrating from B to A. So we can set up this integral. E dot dl, they're both S hat, so S hat dot S hat is 1. Okay, now we have our integral. Pulling out all my constants out front as usual. So when we integrate ds over s, we're going to get a log So when we calculate this, I'm going to change the order to get rid of my minus sign. And now I'm going to use a property of logs to make this a little bit more compact. Log b minus log a is log of b over a. Okay, that's more compact. So now we have an expression for the potential as a function of b and a and epsilon naught and lambda. The reason this isn't a full expression for the potential is because it has lambda in here, and lambda is something we made up. We have to get rid of it in the end. Alright, so we have expressions for the current and we have an expression for the potential. Both of them have lambda in them. Lambda is something that's not given to us, so we need to get rid of that. So our next step is to solve our expression for current and solve our expression for potential for lambda. Okay, so here are our expressions. Let's solve the one for current for lambda. Now let's solve our other one for lambda. Okay, now we want to set these two expressions equal to each other. Alright, well epsilon naught is on both sides, so we can cancel that out. Multiply both sides by sigma L. Okay, now we have an expression for the current. How do we find the resistance? Well, we know from this version of Ohm's law, V equals IR, that resistance equals voltage divided by current. So if we did that, what we get is that the inverse of this expression is the resistance. Alternatively, you might prefer to see it just by rewriting this expression as V equals IR. Whatever way you prefer to think about it is fine. Okay, so does this make sense to you for the resistance? So when B is much bigger than A, log gets bigger. When B and A are close together, log is getting smaller. That makes sense. So the thicker the material between the two shells is, the bigger the resistance is. That makes sense. This says the resistance is proportional to 1 over the conductivity, or is proportional to the resistivity. That makes sense. It says that the longer the cylinders are, the lower the resistance, because that's really creating more area for the current to pass through. So that lowers resistance. So I think that all makes sense. Let me know what you think. So it's kind of cool. It's a little bit tricky because it's not immediately obvious that you want to use this lambda to connect these two expressions. But that lambda that we made up is what connects current and voltage, and lets us put our two results together. So J equals sigma E, once we work out all of our geometry for this specific situation, is always going to give us a V equals IR. So your resistance is going to be a function of geometry and the conductivity. Now I'm going to give you one for you to try. Okay, so here's the one I want you to try yourself. Now instead of having a cylinder nested inside another cylinder with resistive material between them, what we have are nested spheres. So we have an inner metal sphere, and it's just a shell, and an outer metal sphere. They're maintained so that the potential between those two surfaces is V. The material between the two surfaces has conductivity sigma. We want to find the current flowing from one shell to the other. And if we assume that the surface charge on the inner sphere is some positive value S, then we're going to have current flowing from the inner sphere to the outer sphere. So we want to find what that current is and figure out what the resistance of the spherical shell is. Okay, so this doesn't look like a wire. We have current flowing outwards in a sphere. So think of like a Gaussian sphere is your surface area for the current flowing out. Okay, so I've written out all the steps you need to go through to solve this problem. They're the steps I just went through, but I provided you some little hints that have reminders of what you should do. So, instead of assuming we have a charge per unit length, like we did for the cylinder, we're going to assume that the surface charge on the inner sphere is S. Now, previously we've used the symbol sigma for surface charge density, but now we're using sigma for conductivity, so I'm going to use a big S instead. Unfortunately, in physics, we start running out of letters even when we're also using the Greek alphabet. Okay, so the first thing you need to do is figure out what the electric field should be between the shells. Alright, well, you can use Gauss's law to figure this out, or you can take some shortcuts if you're feeling more comfortable. So remember, when you have spherical charge and you're outside that sphere, the electric field just looks like you have a point charge in the middle. That's the total charge. So really all you have to do is find the total charge that's on that sphere and then treat it like the point charge, and that'll tell you the electric field inside that sphere. Now that's something that comes more easily having had lots of practice with Gauss's law, but let me know how you feel about that. So basically, I don't want you to have to calculate these electric fields every time. I want you to be able to use our previous results. But let me know if that's causing you any trouble. Okay, then on step 2, you need to find the current based on your electric field, and I'm just reminding you here the expressions that you need to do that. Then find the potential from the electric field. And remember, you're integrating on a straight path from a point that's B away from the center of the sphere to a point that's A away from the center of the sphere. So the outer sphere has a radius B and the inner sphere has a radius A. So just integrate along a straight line path, like from here to here. Okay, so your results from 2 and 3 are both going to have S in them. So on step 4, I want you to solve each of those expressions for S. Then in step 5, set those expressions for S equal to each other. Then from that, you can do step 6 and 7, where you solve for the current and solve for the resistance. So depending on how you're feeling, you can go ahead and try this whole procedure out by yourself and then come back and check. Or if you want to do one step and check yourself, another step and check yourself, you can do that too, whatever works for you. So we're going to follow the same procedure we just did in my example, but now you're going to do it. This is the only example I'm giving you today because, as you can see, it's kind of a long, involved procedure. Okay, so give it a go. Alright, let's do this. Okay, so the total charge enclosed on the inner surface is just 4 pi a squared s, because s is the surface charge density, and the surface area of the inner sphere is 4 pi a squared because its radius is a. Now you can do integrals to figure this out, but you really don't have to. I hope you're getting more used to doing all these surface integrals and line integrals. But let me know how you're feeling. We've been working on this all semester, but I know it's been an adjustment for some of you. Okay, so we can just treat the Q enclosed just like a point charge. I hope you noticed that whenever you were outside, when I asked you to find, using Gauss's law, I asked you to find the electric field outside, that you just got expressions for point charges. So I don't think I explicitly mentioned that before. Okay, so the 4 pi's cancel out of this. Okay, so there's our expression for our electric field. Now, let's figure out our current. Well, J equals sigma E. So in that case, this is what we get for J. Then the question is, what is our dA? Okay, this is where we have to think about what's the cross-section for the direction current is going. This is a little weird. The current is flowing outwards in the sphere, right? So the surface area, the cross-sectional area for the current, is the surface of a sphere. So on a surface of a sphere, r is constant, but theta and phi vary. And remember, when you're doing spherical coordinates, you get extra terms in here. But I hope you're getting used to this, and you're getting used to using this r squared sine theta when you do this. Alright, and dA points in the r hat direction because it's coming out of the sphere. Okay, so now we can do our integral, j dot dA. R hat dot r hat is 1. If you set these things up correctly, your dot products are always going to do this. Okay, so we plug all that in. The r squared from the dA is cancelled out by the 1 over r squared from the j, from the current density. Theta always integrates from 0 to pi. Phi always integrates from 0 to 2 pi. Okay, we've done these integrals many times. We know the answer comes out to 4 pi. Okay, there's our expression for our current that has S in it. Now let's do our potential. Okay, and we're integrating on a straight line going towards the center of the sphere. So that means R is what's varying. And I apologize, there seems to be construction going on in the building, so if there's any background noise, that's what's going on. I can certainly hear it. I don't know how it's transmitting over the microphone yet. Okay, back to physics. Okay, so we want to plug this into our integral. So we have our expression for the electric field dotted with dr. This looks a lot like the integral we did for a point charge, which makes sense because the electric field outside of the spherical shell just looks like that for a point charge. Okay, so let's do our integral. Alright, and you could, if you didn't want a and b in the denominator, you could find a common denominator and clean this up. I would do something like that, but I'm not going to do it quite yet. Alright, step 4, we want to solve each of our expressions for S. Okay, so I rewrote our expressions for current and potential. Do a little rearranging. Okay, we have both of our expressions. Let's do a little rearranging. Okay, let's set these expressions equal to each other. Well, these epsilon naughts cancel. These a squareds cancel. Now we just need to solve for I for step 6. Alright, at this point having these fractions in the denominator is bothering me, so I'm going to multiply the top and the bottom by AB just to get rid of that. So 1 over a times ab gives you b. 1 over b times ab gives you a. Okay, there's our expression for the current. Then we'll do step 7. Well, I equals v over r. R equals v over I, which tells us then that r should equal b minus a over 4 pi sigma ab. Okay, there's our resistance. Does our resistance make sense? Well, conductivity is in the denominator. That's always a good sign. It says the resistance gets bigger when b and a are farther apart. That makes sense. Okay, so let me know what you do with resistance in your class. I remember my high school teacher taught us an expression for resistance as a function of the length of a resistor and its area, and it had resistivity in it. I'm going to have you derive that for yourselves on your homework. And I'll give you a couple more examples to try in your homework as well. Now, I know a lot of what we do with circuits in the classes, when you're doing Ohm's law, you're working with circuits, you have parallel circuits, we have series circuits, all that sort of thing. And I would love to get into that, and I wanted to do some more complex circuits with you involving capacitors and inductors. However, doing that requires a lot of differential equations. And I did that a little in math methods last semester. We're going to save that for math methods. So once we do differential equations in math methods, we will do some more complicated circuits. And that'll be really fun. Okay, so if you calculate resistance from resistivity in your classes, this will be more relevant to you. But if you're more concerned with series and parallel circuits, well, that's why I gave you a reading assignment related to those topics about teaching circuits in that way. Alright, so tell me about what you do with Ohm's law in your classes. Let me know if this makes sense and what questions you have. Alright, and I'll see you next time.